The requirement that our theory should be local gauge invariant had many consequences. First, it led to the introduction of a gauge field and then to the interaction between fermions through the exchange of this gauge field. And this gauge field must be massless in order for local gauge invariance to be a good symmetry. However, nature showed us that for the weak interaction, the gauge field is massive, and therefore local gauge invariance seems to be broken. So in order to solve this problem, we had to introduce spontaneous symmetry breaking, which leads to the Higgs mechanism, which is a mechanism allowing for the gauge field to acquire a mass through an interaction with a scalar field. So let's review the different components of the final Lagrangian we obtained, which is local gauge invariant even if the gauge field has a mass through the Higgs mechanism. So we started with the Lagrangian, the Dirac Lagrangian for a free fermion, but we showed that this Lagrangian was not local gauge invariant. So in order to restore local gauge invariance, we had to change the covariant derivative into a gauge covariant derivative, and in doing so that introduces an interaction with a gauge field, a mu, and which is a QED interaction Lagrangian. And also, because we have now this gauge field, there should be some kinetic energy associated to it, so we introduced a Maxwell Lagrangian. That means the gauge field is massless. Indeed, if we have a mass term, that will break local gauge invariance. So that's all fine at the level of QED, so that's a QED Lagrangian, because we have a photon which is massless, so the gauge field is massless in the case of QED. However, as we said, in the weak interaction, the gauge field is massive, and therefore we need to add another term to the Lagrangian in order to introduce the Higgs mechanism. This new term is a Lagrangian for a non-Hermitian scalar field, and it introduces a spontaneous symmetry breaking through the fact that the quadratic term has a coefficient which is negative, and therefore the minimum or the vacuum field is obtained for a value of the field which is not zero. The Lagrangian itself is obviously local gauge invariant because we used gauge covariant derivatives in the kinetic energy term. However, the vacuum is not gauge invariant, so that's why we have spontaneous symmetry breaking. We have a phi-4 term in order to ensure that we have a ground state. When we had spontaneous symmetry breaking for global gauge invariant instead of a local gauge invariant, we had a Goldstone boson. However, in the case of a local gauge invariant, spontaneous symmetry breaking does not have a Goldstone boson anymore. So we got rid of the Goldstone boson by requiring local instead of global gauge invariance. Then we expanded the complex scalar field around the vacuum in order to rewrite it as a function of the Higgs field, eta, which is Hermitian, meaning that it has no charge. It is scalar, meaning that its spin is zero, and it's self-interacting because we see we have eta 3 and eta 4 terms appearing in the Lagrangian. And because we use the gauge covariant derivatives, we see that we have a term which is function of the gauge field itself. And this term could be decomposed into three terms. The first one appears to be a mass term, so that's the Higgs mechanism which produces a mass to the gauge field through this local gauge invariant spontaneous symmetry breaking. But we also have two additional terms which involve interaction between the gauge field and the Higgs field. So how does this Lagrangian fit into the big picture? If you look at the Lagrangian for standard model, you will recognize a lot of these terms, in particular the Higgs field, of course, the fermions will be there, their gauge field, the Maxwell Lagrangian, etc. But it will be also more complicated because you have more than one fermionic field. For instance, you have the electron, the muon, the tau, the neutrinos, and also the quarks. And also we only build this Lagrangian based on the U1 group, but there are other groups which contribute in the standard model, like SU3, etc. So that would be just more complicated, but the basic ingredients will be there. One important difference, however, is that you won't see mass terms for the fermions. And that's because these mass terms break chiral symmetry. And all these mass terms, we know that the electron, the muon, the tau have a mass in particular. These mass terms appears also as a coupling through the Higgs. So the Higgs does not only produce a mass for the gauge field, it also produces mass for the other particles in the standard model. In fact, all particles which have a mass interact with the Higgs field because they get their mass through this interaction. This also means that particles which are massless, like the gluon or the photon in the standard model, do not interact directly with the Higgs field. There is one exception of a massive particle, however, which do not acquire its mass through interaction with the Higgs field. It's a neutrino. In the standard model, the neutrino is a massless particle, but we now know that the neutrino has a mass. It's very small. We don't know its absolute value, but we know it has a mass. We know it's there, but we can't explain the mass of the neutrino through the interaction with the scalar Higgs. This means that the standard model is not the ultimate fundamental theory. We already knew that because it does not account, for instance, for gravity, but it also does not account for mechanisms like the mass of the neutrino. So there is now a lot of effort to build a beyond standard model theory which will account for many new phenomena, in particular the mass of the neutrino, but also the dark matter, and ultimately it should include also gravity.